Previously, we learned about something called linear momentum. Linear momentum, which we represented with a letter P, was a vector that was equal to the mass of an object times its linear velocity v. And so if you have some object that has a mass m moving with the speed v, then it has momentum. The faster it goes or the heavier it gets, the more momentum it has. And if there are multiple objects that we're moving around, to find the momentum of the system, you would have to add up the objects together. So if I just have a single particle that has a mass m and a velocity v, then its momentum is given by the equation above. And then you could think of examples where maybe there were a couple of people that are holding their hands together, something like this. And maybe they're on some skateboards, or maybe they're on ice skates, and they push apart. So the initial momentum of the system was 0 because they weren't moving, they were just sitting there holding hands. So the velocity of each one of those people initially is 0. And then let's say after they've been sitting there for a while, they push off of one another. They exert equal forces on one another. And then the person on the left starts moving with a velocity v, and they have a big mass m. And then the person on the right starts moving with a bigger velocity v because they have a smaller mass m. But the products m times v going to the left and m times v going to the right should be equal. So the masses aren't equal, the velocities aren't equal, but m times v on each side will be equal. So that way the momentum of the first person and the momentum of the second person are equal. And the way that we dealt with problems like this is we said the initial momentum was 0 because neither one of the objects were moving. We could write m times 0 plus m times 0 if we really wanted to. The final momentum now, because momentum is a vector, if we decided to call to the right the positive direction, then the person number 2 on the right would have a positive momentum, and the way we would write that is little m big V, positive momentum, and then P1, which goes to the left, the momentum of the person on the left, would be a negative momentum because momentum is a vector, and they're moving to the left. So that would be minus big M times little v. And based off of what I'm telling you, the products of m and v on each side need to be the same, and so the momentum would add up to 0. And so what we would say is the initial momentum was 0, and the final momentum was 0, and so the change in momentum, delta p, was equal to 0. And the reason why the change in momentum was 0, or at least in practical senses would be approximately 0, would be because there was no external forces that were acting on the system. So we could say that the net external force acting on the system was equal to 0. This is the condition for the conservation of linear momentum. As long as we have a net external force of 0, then momentum is conserved. The flip side of that then is, something's moving along with a momentum p, and I push it, or if some force is acting on it to speed it up or slow it down, then the net external force isn't 0, and the momentum of that object can change. The other thing that we dealt with was the reason why we have to say the net external force. We saw an image of a guy on the back of a truck trying to push the truck from inside the bed of the truck, and we called that an internal force. And I said that internal forces can't change the linear momentum of a system. So somebody standing on the bed of a truck trying to push on the back of the truck from the inside, since that's an internal force, it can't speed up the truck. And so only external forces can change the linear momentum, which means as long as the external force, the net external force, is 0, then the change in momentum will be 0, and we'll have situations like this, where momentum is conserved. The last thing I'll say about linear momentum is that if momentum has an equation of m times v, m has units of kilograms, and velocity v has units of meters per second. And so our unit for momentum was kilograms meters per second. That was it. There wasn't another unit that redefined the way we write that unit. It was just kilograms meters per second. Now we're going to define a new quantity, angular momentum, that's very similar to linear momentum. And we're going to start by talking about how an object could have an angular momentum. So we're going to imagine there's a rod here that's like a massless rod. And on the end of that rod, there's a particle with mass m. What I mean when I say a massless rod is the mass at the end of the rod, that particle with mass m, it is much heavier than the mass of the rod itself. And the reason I want to do that is because I'm trying to focus on what would the angular momentum of just that point mass be. I don't want to worry about the angular momentum of the rod itself, which is something that we'll have to come back to later. But we're just going to focus on this mass m, and the rod is there to help you realize how the thing would be moving around. So maybe there's an axis of rotation on the left end of this rod, and the rod is rotating with an angular velocity omega. Because of the angular velocity omega, and due to the position of the point mass, that point mass is going to have its own linear velocity v, right? V equals r omega, so the further that mass gets away from the axis of rotation, the larger that linear velocity gets. But because of the rod rotating, it has a linear velocity v and an angular velocity omega. Because of that linear velocity, it has an angular momentum. With respect to that axis of rotation that I've defined on the left, the object moves angularly, and because of that angular movement, it has what we call an angular momentum. We're going to define the angular momentum in this way. Angular momentum, for which we use the letter L, a capital letter L is used for angular momentum. Angular momentum L is equal to r perp times p, where p is the linear momentum of the object, which makes some sense, right? If an object has more linear momentum, it makes sense that it'll have more angular momentum. And then r perp is the same r perp that we dealt with when we were calculating torques. R perp is this distance, this perpendicular distance from the axis of rotation to the object, right? So here it goes from the axis of rotation, the left end of that rod, to the right end where the mass is. So r perp times p gives us the angular momentum. And now what I'd like to do is take this equation for linear momentum and express it in a way that is going to help us a lot more in terms of problem solving. So L equals r perp times p. I know that because of the way I've defined r perp for the picture on the left, that r perp is just equal to the length of that rod, and so instead of writing r perp, I'm just going to write r. And we know that from above, linear momentum is equal to m times v. We also know that linear velocity v of the point mass at the end of the rod is equal to r times omega, right? V equals r omega, where if r increases, v increases. So I'm going to substitute in on the right side now. We'll have rm times v, which is equal to r times omega. So that could be rewritten as mr squared omega. And a part of that should look familiar to you because mr squared is the equation for the moment of inertia of a point mass, right? If I have a point mass, an object where all of its mass is concentrated at one point, the moment of inertia of that kind of object is just mr squared. There's no number out in front. So I could write this equation that I have now as the moment of inertia, I, times omega. And this is one of the ways that we'll typically think of angular momentum. Angular momentum, L, is equal to moment of inertia times angular velocity. And if you think back to when we were learning all the differences between the translational and rotational quantities, I said that there's a long list of analogous quantities, right? On the left we have the translational stuff, on the right we have the rotational stuff, and all those equations turn out to be quite similar. And here we have the same. If you look back up to my equation for the linear momentum of an object, which was P equals m times v, now we have an analogous kind of thing for angular momentum. We use L, and I replace m with the rotational equivalent to m, which is I, and we replace v with the rotational equivalent to v, which is omega. Angular velocity is a vector, so I should write that angular velocity is a vector, which means, of course, then angular momentum is a vector. And so hopefully you can see the similarities and the differences between linear momentum and angular momentum. Linear momentum had units of kilograms times meters per second. So kilograms meters per second. So what are the units of angular momentum? Well, moment of inertia is an mr squared type of thing times omega for the whole linear momentum. So what should I write? For the mass, it is kilograms. R is a distance, so that would be measured in meters, and it's squared, so I should square that. And then omega is radians per second. But as we've said previously, radians is more of a placeholder than it is a way of defining what the unit is. And so the way we'll think of the units for angular momentum is just kilograms meters squared per second, where omega needs to be measured in radians per second, but that's just like an understood thing. So kilograms meters squared per second is the unit for angular momentum, and you need to make sure, as previously, that you convert all things into radians before you figure out what omega is. Now what I'd like to do is look at an example where we try to find what is the angular momentum of this system. So if we know that the angular momentum of any system is given by I times omega, then when I say find the angular momentum, what I mean is find the moment of inertia of the system and multiply it by the angular velocity of that system. And in this system, the way that I'm going to treat the system is there are 3 point masses, so the 3m, the m, and the 2m, and the rod is massless. So if the rod were not massless, which means that if the rod had a mass that was on the order of the same size as the masses that are attached to it, then I would need to include that in the moment of inertia of the system. But here I'm just working with the point masses. You should know and remember that for a point mass, the moment of inertia for that kind of object is mr squared. There's going to be instances where that might not be given to you. So the moment of inertia of this system, I need to add up or sum up the moment of inertia of all the individual point masses. And the way that we do that is we'll just start on the left. So the mass of that object is 3m, and it is a certain distance away from the axis of rotation, which I've defined as just being x. So it's 3m times r squared, and here instead of r, the variable that I've used for distance is x. So it's 3m x squared. Plus, on the right now we have an object with mass m, and it is a distance x away from the axis of rotation, so again x squared, plus the moment of inertia of the mass at 2m. So the mass is 2m, and the distance from the axis of rotation to the mass with 2m is not just x, but it's 2x, because each of the segments that I've drawn are a length of x, and so it's a distance of 2x. So 2x squared. So the moment of inertia of the system, the whole thing, would be 3mx squared plus mx squared plus, and then in the last term, 2x squared is equal to 4x squared, and 4x squared times 2m would give me 8mx squared. And since all of those terms are in terms of mx squared, I can just add them all together. So 3 plus 1 plus 8, that's 4 plus 8, which is 12. So 12 mx squared. Using my equation for angular momentum now, the moment of inertia is 12 mx squared, and the angular velocity was given as omega, and so my expression for the angular momentum is just 12 mx squared omega. And so this equation would be the answer to a type of question where I ask you to derive an expression for the linear momentum of that system. But much more important than that answer is to think about how we get angular momentum and when it's greater, when it's less. So when I have an object moving linearly and it has a linear momentum, if it has more mass or more velocity, right, if it speeds up, then it's going to have more linear momentum. If I have a system rotating with an angular velocity omega, and I have all these point masses on there, then each one is contributing some angular momentum. Because if I spin that thing with angular velocity omega, it's going to be harder to spin the more mass I've got, so I have more angular momentum. It's going to be harder to spin if I take some of those point masses and move them further away from the axis of rotation, right? It's more difficult to move stuff when it's further away from the axis of rotation. Similarly, if that thing was moving along with an angular velocity omega, and I could take the mass with 2m and slide it closer towards the center of the axis of rotation, then the thing would speed up. And so the angular momentum of a system depends on that mass distribution, where all of those point masses are, and what the angular velocity is going to be. And so if I start playing with the positions of the mass 3m, the mass m, the mass 2m, then I'm messing with the moment of inertia values, and by consequence, I'm messing with the angular velocities. So something that I'm going to introduce right now, but I'm not going to talk about in too much detail, is what we learned at the beginning of this rotation unit, and what is now going to pull all this stuff together. Like linear momentum, angular momentum is a quantity that is also conserved, the conservation of angular momentum. And the way that I can write that is I can say that the initial angular momentum is equal to the final angular momentum, right? So I times omega equals I times omega, where we have an initial moment of inertia and angular velocity, and then a final moment of inertia and angular velocity. And if that moment of inertia decreases, then that angular velocity will increase. Right? So you could see a clear relationship between those two variables between two different points in time. And so similar to the way that we had the net external force needing to be 0 in order for linear momentum to be conserved, in order for angular momentum to be conserved, which would be delta L equals 0, in order for the linear momentum not to change, it's not the net force that needs to be equal to 0, but it's the net external torque that needs to be equal to 0. If the net external torque is equal to 0, the linear momentum cannot change. It doesn't mean that the moment of inertia or the angular velocity independently doesn't change. It means that the product, I times omega, does not change. And so, similar to the way that if an object is moving in a straight line and I push on it, then I can increase its linear momentum. I can, as an external torquer, I can go up to this rod and make it spin faster if I want to, but that's an external torque. But so long as there's no external torque acting on this rod as it spins around, then the linear momentum won't change. The last thing that I'd like to do would be to just very quickly summarize what we've talked about so far. Conservation of linear momentum. We know that linear momentum is P, which is equal to m times v, and in order for linear momentum to be conserved, we say that if the net external force is equal to 0, then delta P is equal to 0. And then similarly, for angular momentum, we know that angular momentum, L, is equal to I times omega, and if the net external torque is equal to 0, then delta L, the change in angular momentum, will be equal to 0. There are lots of problems where delta P or delta L equals 0 is going to be the way that we'll solve the problem, because linear momentum or angular momentum will be conserved. But what happens in cases where the external force or the external torque isn't equal to 0, when there is an external force or torque that's causing the thing to speed up, slow down? When we studied momentum, we said that there can be a change in momentum, and that change in momentum was equal to the external force that was applied times the time interval over which that external force was applied. And we said that that external force over that time interval was exerting an impulse on the object, and that impulse causes a change in momentum. So momentum can change, and it's given by this equation. So there should be an analogous type of equation for angular momentum. The angular momentum of a system can change, delta L equals, as long as there's an external torque that's applied. That external torque is tau, and that torque is going to be exerted over a certain time interval. So I've replaced external force with external torque. Okay, so this is kind of like the angular equivalent of impulse, right? Something that could speed up or slow down a system. I would strongly encourage you, as we wrap up here, to take out your equation sheet and find the equation for angular momentum, I times omega, and find the equation for a change in angular momentum due to a net external torque. They're both on there, and you need to know where they are.